Okay, so observe, if you plot sine and cosine against one another, here's the graph of, sorry, let's go back. Here's the graph of sine. If I plot cosine in red, it looks just like this. Okay, in other words, cosine appears to be the same curve but horizontally shifted, and it is. Okay? The sine curve can be seen as a horizontal shift of the cosine curve and vice versa. By how much? Exactly 1 quadrant, or pi over 2. So observe, what does the y-coordinate do? It starts at 0 and starts going up. That's the same thing as if I had started at this angle 1 quadrant earlier and looked at the x-coordinate. It starts at 0 and starts going up. Here the y-coordinate goes down from 1 to 0. Here the x-coordinate goes down from 1 to 0. Here the y-coordinate goes from 0 to -1. Here the x-coordinate goes from 0 to -1. They're doing the same things, but delayed by 1 quadrant, and that's expressed in this formula right here. Okay. So a sinusoidal function is something that looks like this. The amplitude is the absolute value of the number out in front, and the amplitude represents the range is going to be from -a to a. Negative amplitude to amplitude. Sorry, a doesn't have to be positive, but the amplitude does. So the range is trapped between these two numbers. As soon as you do a horizontal compression or stretching by omega, the original period was 2 pi, but we've compressed by a factor of omega, so now the period is exactly 2 pi over omega. That's how long it takes to repeat itself. So determine the amplitude and period of this function. Well, it's pretty straightforward. Okay. The amplitude is just the absolute value of the number multiplying the trig function, is 5. The period is 2 pi over the number multiplying the input, which is 3, so 2 pi over 3. So we can use information like this to draw this graph using what are called key points. So determine the amplitude and period. Well, the amplitude is just 2, and the period is exactly pi. It's 2 pi over that 2 that's inside the parentheses. Okay. So we know the amplitude is 2, so everything that happens between y equals -2 and y equals +2. And the period is pi, so I can draw a complete cycle going from 0 to pi. So what I like to do, and the book does the same thing, I know the period is 2 pi over omega. If I divide this into quarter periods, that would be 2 pi over omega over 4, aka 2 pi over 4 omega, aka pi over 2 omega. This is now 1/4 of the period. Because what do the original trig functions do in quadrants? They go from, for example, let's look at sine. Sine goes per quadrant from 0 to its max, to its 0, to its min, to its 0, and then it starts repeating. What does cosine do? It goes from its max to its 0, to its min, to its 0, to its max. So every quarter period tells me a nice range of motion from my 0 to my maximum or my minimum, or vice versa. So what you do is indicate how long that is. What is 1/4 period? Okay, so in this example, the period was pi, so 1/4 of that is just pi over 4. So I just start marking off. This is a confusing way of writing it. Okay, I would just say, we know that generally the graph starts at 0. I start marking off quarter periods. 1/4 pi, 2/4 pi, 3/4 pi, 4/4 pi. This is now 1 complete period. Okay. Also, we happen to know that the maximum value, because remember this was y equals 2 times the sine of 2x. Was it sine or cosine? I'm going to flip back quick. I forget. Okay, back to where we were. Sorry. So I know that the maximum it's going to reach is 2, and I know that the minimum it's going to reach is -2. So now what does the sine function do? In 1/4 period, the sine goes from a 0 up to its max. So our graph, and I'll switch over to a different color for clarity, our graph is going to go from its 0 up to its max in 1/4 period. Quarter period. In the next quadrant, in the next quarter period, the sine curve goes from its maximum back down to being 0. Then it will go from 0 to its minimum. Then it will go from its minimum back to 0. So here is a nice graph of this just based on the fact that we knew its amplitude was 2 and its period is pi. Okay, so let's clear off my picture and see what theirs are. So they simply evaluate them at each of these points, which is all I did, knowing those were going to be a 0, a max, a 0, a min, and 0 again. And then they link them up with a sine-looking curve. Okay. You can then continue this picture many times because you know it's periodic, so you just have to repeat the same picture. So switching back to red, because now they're drawing in blue. Our original picture was exactly this much. And now I just repeat it, do it again to the left. And you can just keep repeating this figure over and over again. Because remember, the domain is all real numbers. So the graph does keep going on forever. Okay. So let's do another one. Y is 4 times the sine of negative pi over 4x. Now the very first thing we want to do, I don't want to say the following. I don't want to say amplitude is the absolute value of 4, which is 4. That's fine. What I don't want to do is say that the period is 2 pi over omega. That's 2 pi over negative pi over 4, which reduces down to negative 8. It doesn't make any sense to have a negative period. So the first thing you need to do is exploit even-odd properties so that the number multiplying x is not negative. So the first thing I'm going to do is use the fact that the sine function is odd and call this negative 4 times the sine of pi over 4x. Now I can say the amplitude is the absolute value of negative 4, which is 4. So in my graph drawing, whatever happens, it's trapped between y equals 4 and y equals negative 4. Okay. Now what's my period? 2 pi over 4, which is 8. I also am interested in what's 1/4 of the period. Well, 1/4 of the period is just going to be 2. So I come over here and I'm going to put down my axis of x equals 0. And I'm going to mark off quarter periods, 2, 4, 6, 8. I can even go backwards, -2, -4, just because I had the space. Now what I need to do is just start marking off every quarter period. What does the graph do? So normally, the sine curve would go from its 0 up, but this has a negative sign in front of it, so it's reflected. So it goes from its 0 down to its minimum in 1/4 period, back up, up, down. And I can continue this picture back here as well. So there's my graph of 4 times the sine of negative pi over 4 times x. First step, you don't want a negative sign inside your argument for sine or cosine, so use even or odd properties to pull it out for a sine function or ignore it completely for a cosine. Find your amplitude. You're trapped in between those two lines. Find your period and therefore your quarter period and mark those off, and then use quarter periods to just say from your middle value to your max to your middle to your min, whatever it is, depending on whether you're doing sine or cosine. Okay, so they just do the same thing. They compute period of 8, or they divide it into segments of length 2, and then they find these coordinates 2, 4, 6, 8. They evaluate it at those particular points, 0 to the min, to the 0 to the max, to the 0. And they label those key points and graph them. It's really the same work we had done. Okay. You can then extend it. Cool. So in the next video, we'll come back and we'll just keep doing more examples like this. Okay, but generally what you should be able to do is draw a graph of anything that looks like a sine of omega x, where a can be any real number and omega can be any real number, positive or negative. And you should also be able to do it for a cosine curve. Okay. The only thing that changes is a sine curve. If a is positive, looks like this. If a is negative, it looks like that. For a cosine curve, assuming, sorry, you're starting at x equals 0. So this is a positive sine curve. This is a negative sine curve. Starting at x equals 0, a positive cosine curve looks like this. But a negative cosine curve starting at 0 looks like this. It's just reflected. Okay, so after this, we'll come back and we'll start looking at more graphing problems.